All right, folks, so we want to take a look here at velocity versus time graphs. And again, these are a little bit different than the previous graphs that we were just working with, those position versus time graphs. So we're going to set up a graph that looks very similar to what we had before, but it means a slightly different thing than what we had before. Before we had a position time graph where it was sort of telling us where something was at any given point in time. Here we have a velocity time graph, which tells us how fast something is going at any point in time. So whereas before, in the position time, this flat section would have been no movement, instead here, it is a constant movement of 30 meters per second, right? We've got a y value of of velocity, so it's 30 meters per second along this whole section there. And just like before, we want to be able to do two things with this graph. The first is to find acceleration, or average acceleration. And that is going to be our slope here. So because, again, we've got meters per second here, and seconds as our time, if we take our rise, which is our y values, over our run, that gets us meters per second squared, which is a value for acceleration. So let me switch that back up there. So for example, if we wanted to know what the acceleration was from 10 to 20 seconds, my acceleration would be, kind of mark that off a little bit, my change in velocity over our change in time. My velocity goes from being 30 meters per second at the beginning to 0 meters per second at the end. I lose 30 meters per second. I change it in the negative direction, 30 meters per second. And that takes us a total of 10 seconds, which means my average acceleration is going to be -3 meters per second squared. So I just took the slope. I took the final position, or the final y value minus the initial y value, divided by the final x value minus the initial x value. If I wanted to know the average acceleration of the whole trip, I would just take those values that are for the whole trip. I would take this and this as my y and x initial and final values. So there I would say, all right, my final velocity is 0, I'm at the x-axis, minus my initial of 30, divided by my final time of 20, minus my initial time of 0. -30 over 20 is -1.5. And you'll notice from the last video that we got these same numbers, but here they mean different things. Whereas those were our average velocities from the previous graph, these are average accelerations here with our velocity time graph. And the last thing we want to be able to do is get the displacement from this graph, and we do that a little bit differently. Let me go ahead and mark some of these again, 10 seconds and 20 seconds, and 30 meters per second. We've got velocity and time. So to find displacement, we have to take the integral of this graph. So that is the area underneath the curve. So when we talk about the area underneath the curve, that is the area that is between the x-axis and our slope, and our graph. So if I wanted the entire displacement for this entire trip, I would need to find the area of this entire shaded section. But I want to just do this first piece first, just from 0 to 10 seconds. And if you'll notice, as I sort of outline that, that is a rectangle. So we are just doing the area of a rectangle, which is just the base times the height. So here, this base is 10. We go from 0 to 10, multiplied by the y value, 30. So my area here is 300. And remember that our displacement is meters. So that area is 300 meters. And that makes sense. If I go at a constant speed of 30 meters per second for 10 seconds, I'm going to go 300 meters. I'm multiplying my velocity times time. If we sort of rearrange this equation, velocity is displacement over time, our displacement is just our velocity times the time. So if I take the velocity, multiply it by the time. As long as that velocity is constant, I'm just multiplying those two together. Here in this section, that velocity isn't constant. We've got this acceleration, but we can use a little geometry to still get that area. You'll notice that that is a triangle that has been poorly drawn. It's got a little curve to it, but ultimately that is a triangle. The area of a triangle is 1/2 base times height. So we do the same thing here. If I want the distance or the displacement from 10 to 20 seconds, I have a half times still the base of 10, and that height is still 30. But because it's a triangle, we take half of that, so I end up with a displacement of 150 meters. If the question then asks what's the displacement for the entire 20-second period, I would just take this displacement, the 300, and I would add 150 to it. So for the whole thing, we're looking at 450 meters. So again, we want to be able to do two things: get the acceleration or the average acceleration by taking the slope of this graph, and we want to be able to take the integral, that area underneath the curve, to get the displacement. Both of those are necessary for the quiz.